Okay, hello everyone in a new video. So we have reached part 2 of chapter 5, which is mainly chapters 5 and 6, and eventually we have reached section 4, which is the tension force. Then in order to introduce the tension force, we need to consider the following experiment. So suppose we have a support, so this support may be a ceiling. So from one end of the and let's consider a string in which from the string has two ends. So here by the string I mean a rope, and from one end of the string this is connected to the support, and to the other end we connect a solid S. So let me say that this is the solid S, this is the string is considered as a rope, and let's label the following points. So this is the point A, and this is the point G. G is the center of gravity of the solid S, and A is the point of contact between the string and the solid S. So here in this case the solid S, we can consider it to be a ball. Now this solid S, it has a mass. Because it has a mass, then it will be directly subjected to the weight W. So S is submitted, let me say, is under the action of its weight W, because it has a mass. So any object having a mass will be directly subjected to the weight, which is vertically downward like this. Now because the weight is classified as a force acting at a distance, then it will be acting at the center of gravity G. This is the weight W. Then we expect that that S must fall down, or let me say, instead of saying fall down, okay, so it must fall down due to the action of the weight but what is preventing us from falling down is the string, okay, and this string is connected to us at the point of contact, which is the point A. Now we need to explain this at the level of the forces. So how one can explain this at the level of the forces? So in order for us not to fall down, there must be another force which is balancing the effect of W, or it cancels the effect of W. So we will say the force exerted by the by the string on the solid S is given by the tension force. Okay, so the tension force T is the force preventing S from falling down. Now what are the properties of this force? Let me say properties of T. Or before we start listing the properties, let me classify T, because the classification is important. Classification of T. So in this case, what is the classification of T? And by the classification of T, I mean that we need to say whether T is a contact force or acting at a distance. Recall that the only three forces that act at a distance are the weight, the electric, and the magnetic, and all other forces are classified as contact forces, and in particular the tension T. And here T is for tension, and we don't forget the vector. Then T is a contact force. Now we are ready to list the properties of T. And let me start directly by the point of application. Line of action. The direction. And the magnitude. Okay, so because T is classified as a contact force, then the point of application will simply be the point of contact. Okay, so but here about which point we are talking, which point of contact? So we are talking about the point of contact between the two bodies that are at interaction, and they are given by the string and the solid S. And notice that they meet, or they are in contact, in which point? At the point A. Okay, so this is the first property regarding the tension T. So how do we know that the point of application is the point of contact A? Because it is due to the string connected to us, and they are connected at the point A. What about the line of action? So the tension T always act along the string. Now in this case, what is the line of action of the string? So this is vertical. What about the direction? So recall that we have introduced T in order to cancel the effect of W, or to balance W. So if it is acting along the string which is vertical, it may act like this upward, or even like this downward. If it's acting downward, then the solid S must fall down. So in order for the solid S to remain at equilibrium like this, it must act vertically upward. Okay, for this reason, the direction is upward, And as for the magnitude, now I leave it to be empty. Later on we will discuss how to calculate the magnitude of the tension. And here what I want to say is that I will place the following in boxes. Now regarding the tension force, all of these properties, so the point of contact will remain the same, along the string will remain the same. What will change is that what I have placed in a box. So when solving exercises related to tension, here our answer will differ only in the answers that I have placed in a box. So instead, for example, another exercise, instead of placing A, we will place B, for example. Instead of being vertical, it will be oblique. Instead, for example, being upward, it will be upward to the left, etc. Okay, so the answers that I have placed in a box, they will change. As for the other answers, which is the point of application, the point of contact, the line of action along the string, etc., they will not change. And also let me make the following note that we will use now. In order to convert from grams to kilograms, we simply divide by 1000. And converting from kilograms to grams, we multiply by 1000. So this is an important one. Okay, so from kilograms to grams, we multiply by 1000 because we are all familiar with the fact that K from the social media is given by 1000. Then going from grams to kilograms is simply divided by 1000. And for the sake of this section, let me consider the following application, which is application 2. And let me say that a solid S is suspended from the free end of a string or let me say this a solid S of mass is suspended from the free end of a string and take G is equal to 10 newtons per kilogram. So what does the value of G represent? The value of G reflects the planet on which we are performing this experiment. Okay, so G is equal to 10 newtons per kilogram. It means that we are performing this experiment on the surface of Earth. If G is equal to 1.6 newtons per kilogram, for example, it means that we are performing this experiment on the surface of Moon, etc. Okay, so this value here reflects the planet on which we are performing the experiment. Okay, so let's consider that this is the support and this is the string and this is the solid S that is attached to the free end of the string like this. Okay, and let me give this point to be the point C and this point, sorry, let me say that this is the point D, for example, and this is the point G, this is the solid S, and this is the support. Okay, so this shaded part, it means that you are not interested what is above or what is the type of the ceiling. Okay, and let me pose the first question, which is given by what are the forces acting on us. And now number 2, classify the above forces. Number 3, so let me say even classify the above forces into acting at a distance or contact forces. Now number 3, list the properties of the above forces. And now number 4, so let me say list the properties of the above forces knowing that they have the same magnitude. And now number 4, represent the above forces using a scale of 1 centimeter corresponding to 1 newtons. Okay. So let's start by answering the questions. Now in number 1 they are telling me, let me answer them in blue. What are the forces acting on us? So the first force that we always should consider is the weight, because basically any object have a mass. Because this solid S have a mass given by 300 grams, then it will be directly subjected to the weight W, to its weight W. So what does the weight W represent? It is the force exerted by Earth on the solid S. And here, because we have a string, then it will be directly subjected to the tension T. Now in number 2, they are telling me classify the above forces into acting at a distance or contact forces. So we know that the only 3 forces that act at a distance are given by the weight, the electric, the magnetic, and here with no exception the W is classified as acting at a distance. And all other forces are classified as contact forces, and in particular the tension T. Now in number 3 they are telling me to list the properties of the above forces. So we need to list the properties of the weight and the properties of T, knowing that they have the same magnitude. Okay, so always we start by listing the properties of W, because we need to deduce T from W. Then let's start by listing the properties of the weight W. So properties of W. And by the properties I mean the point of application, the line of action, the direction, and the magnitude. So let me start directly with the point of application. Line of action. So because W is classified acting at a distance, then the point of application will be the center of gravity, G. Always the point of application of the weight W is the center of gravity, G. As for the line of action, we know that always the weight acts vertically downward, so this is vertical and this is downward. So always the 3 properties of the weight, they will never change. As for the magnitude, we know that the magnitude can be calculated via the following formula, that the weight is equal to m multiplied by g. Now here the value of m is given to be 300 grams. So m is equal to 300 grams. We know that grams is not the SI unit of mass. In order to convert from grams to kilograms, we simply divide by 1000. Then 300 divided by 1000. So this is equal to 0.3 kilograms. So this is equal to 0.3, the mass that we have computed here, multiplied by the value of g that is given above, and the value of g is given by 10. Now plugging this on the calculator, so the value of w is given by 3. Since this and this are expressed in the SI, so the value of w will be in the SI, which is in newtons. Then w is equal to 3 newtons. And as you can notice regarding the properties of w, so regarding these three properties, they will never change except for the weight, the magnitude of the weight. Now we can directly deduce the properties of T. Now let me say point of application. So because T is classified as a contact force, I will say it's a point of contact. And as I have mentioned previously, that the line of action will not change until it is given by along the string. The direction is still this moment unknown, and the magnitude is also unknown. Now how shall one determine what is the point of contact, what is this, what is this, and what is this as well? Now referring back to the document, we can notice that the point of contact between the string and the solid S is given by the point D. Now along the string means that the line of action is the same as that of the string, so notice that in this case the string is vertical. Now what's the direction of T? T must oppose the action of W, so if W is downward, then T will be upward. And in the question they are telling me that, knowing that they have the same magnitude, so if the magnitude of the weight is 3 newtons, then the magnitude of the tension is equal to 3 newtons. And here notice that whenever we are discussing magnitudes, we don't place the vectors, okay, because the magnitudes are numbers, and whenever we are placing numbers, no need to place the vectors. Whenever we are talking about properties in general, we place what? The vector. Okay, so whenever we are talking about properties in general, we place the vectors. Now in number 4 they are telling me to represent the above figure, represent the above forces, and here they are talking about the weight and the tension using a scale of 1 centimeter of 1 newtons. So let me place the scale here, knowing that 1 centimeter corresponds to 1 newton, and you are interested in representing these forces. Now in order to represent these forces, the first thing that we should do is reproduce the figure. Okay, so what is important is just to reproduce the solid S, no need to reproduce another stuff. We don't care about the support and we don't care about the string, okay? So or we can, for example, represent the string, it's not a big deal, so this is the string like this. Okay, and now I will represent the forces using another color, let me say in blue. Okay, now okay, And let me say that this is the point D and this is the point G. Let's start by the presentation of the weight. So in order to represent the weight, we need to draw it. Representation means drawing. And in order to represent the weight, we need to determine the length. However, here we don't know the length, we know the magnitude, and we know that the connection between the magnitude and the length is given by the scale. Placing here 3 newtons, which means that 3 multiplied by 1 divided by 1 is equal to 3 centimeters. What does this number represent? This number represents the length of the vector W according to this scale. Now in this case, we drag the ruler from the point G exactly 3 centimeters downward. This is the head of the vector. The length of this vector is given by 3 centimeters, worth 3 newtons according to this scale, and the name of this force is given by W. Now regarding the tension T, and here notice carefully that I have represented the weight. The tail of the vector is starting from the point G, because as I have stressed earlier, that the point of application is the center of gravity, G. Now regarding the tension must be drawn from the point of contact D along the string vertical upward. The magnitude of the tension T is given by 3 newtons, which is worth 3 centimeters. So you can repeat the calculation and check that it will be given by 3 centimeters, but no need to repeat it. So we drag the ruler. So this is 3 centimeters. Okay, the name of this vector is tension T, worth 3 centimeters, given by 3 newtons according to this scale. And notice that I have represented the vector D starting from this point, because this is the point of application of T, which is the point of contact between the two bodies that are at interaction, which is given by the string and the solid S, which is considered as a sphere. So that's it for me in this video, guys. In the next video we will discuss the normal reaction and also consider another application which clarifies the different properties of the normal force.